Okay. Welcome to our third RCA Lunch and Learn session. I'm Steve McCormick. I'm chairman of the Railway Civil Engineers Association. I'm also a principal engineer for Network Rail, working on the Transpennine Route upgrade. Previous Lunch and Learn sessions, we've included approach to fire safety design at station schemes, use of tactile pavings at station, and today's Lunch and Learn covers the subject of track-bridge interaction. Just a little bit about the Railway Civil Engineer. We were formed in 1921 and we exist to encourage and exchange the knowledge and experience of railway civil engineers. In 1997, following privatisation of British Rail, the RCA became a specialist knowledge society of the Institution of Civil Engineers. We work closely with other engineering disciplines through the Railway Engineers Forum and the Young Railway Professionals. And currently we have over 400 members, and we have a programme of 10 events held at Great George Street and regional meetings. These Lunch and Learn sessions are in addition to these 10 events. If you need to gain access to us, just Google RCEA and you'll find our website there. In terms of membership, we've just had our AGM. We've agreed to maintain the fees again for 2024. So it's £18.50 for an ordinary member, £8.75 for a young professional member, retired members £5.50, and it's free to student members of the ICE. If you fancy getting involved, our next committee meeting is the 28th of May at 5 p.m. and that will be online. The meetings, we look at future events and also the direction of the RCA. If you're interested in getting involved, that's becoming a committee member or getting involved in organising any meetings, please email us at the email address there. Thank you. Future events, we've got today's Lunch and Learn, which is Track Bridge Interaction. On the 23rd of May, we've got a hybrid event in London at Great George Street, which is Hammersmith Bridge, stabilising a 137-year-old wrought iron suspension bridge. And then on the 11th of June, we have another Lunch and Learning session, which will be the importance of temporary works. Today's event is an online session which describes the basic principles of track bridge interaction, including calculations related to situations in which continuous rail span discontinuities in their supporting structure. Presentation will make reference to the relevant clauses of the Second Generation Eurocode and will also outline approaches which may be used for cases which differ from examples in the standard. Today's speaker is David Rhodes, who's an independent consultant. David has worked in the railway industry since 1983. From 2003 until 2013, he was technical director at Pandrol Rail Fastenings. Since then, he's worked as an independent consultant, advising various clients on track components design issues. David was also served on the British, European and international standards working groups, including acting as chairman of a CEN Task Group on track bridge interaction between 2015 and 2018. And now if I can hand you over to David, if I stop sharing.
Right. Well, good afternoon, everyone, and let me try and work the magic of sharing on my computer. So we should be. Has that appeared on anyone's screen? I can't tell from here.
Yeah. Nothing yet.
Nothing yet, no.
Right, let me share. Right. I think that might. How about that?
No.
Not yet.
Not yet. Having tested all of this out on my new laptop, I'm now struggling. Let's have a look. Still no?
Nothing there yet. Sorry, David.
No,
That is very curious.
that is very curious. Hang on. I'm pressing screen content only. Opening PowerPoint.
David, when you
Presentation mode, David.
Yeah, I'm in presenter mode. Content only, it says, which I thought was.
when you click share, it should open up all the screens that are open, and you can click on whichever one you want to present from.
This is embarrassing.
Oh, that's doing it.
We there?
Yeah, we've got your team screen and your.
All right. Have you got the PowerPoint screen now?
Yeah.
Yeah.
All right. Hooray.
Perfect.
Okay. Right. So I come to you today as an expert on trap bridge interaction who knows nothing about how to work a PC. But anyway, we'll start from that point. So trap bridge interaction. It's a bit of a code word for something a bit more complicated, but specifically what I'm going to talk about today is this issue of how we deal with conditions where continuous rails are spanning across discontinuities in the supporting structures. So things like structural movement, joints, or bridge deck ends. What I'm going to do today is talk mainly about general principles. I'm not going to get into the details of any calculations. And the other thing to say is that I'm going to, in most cases, be talking about the effect on the stress in the rail. If you jump into this subject in full detail, it has effects on things like bearing forces and so on as well. But in the interest of keeping to the time, I'm going to mainly focus on what does it do to the rail stress, and you can think through yourselves what it does to other things. Another thing to mention right at the beginning is that the current standards focus mainly on conditions for high-speed and mainline tracks, and that will come into why that's important later on. Why is this an issue now? And we've been building railways on bridges for almost 200 years, and it's suddenly become an issue of great interest. Main reason is this: if you look at the top left picture, the traditional brick arch viaduct, for example, bridges were built first of all massive rigid structures with fairly short spans, maybe 15 meters between piers. And then on top of that, we put a track which was on stone ballast, wooden sleepers, jointed rail, carrying relatively low speed trains. And the result is that the bridge hardly moves. And if it does move, there's enough play in the track, enough sort of rattling fit in the track for the track to adjust itself to any changes of bridge geometry. And even on the right-hand side of the trestle type bridge there, again, fairly short spans, quite a rigid structure despite the open spaces in it. And the kind of track structure that was put on top of those originally was a fairly loose fit. So if the bridge moved, the track could accommodate the movement. What we do nowadays is things like these two. These are a couple of examples of bridges on high speed lines. Top left is in Korea and the bottom right is in Germany. So we've got much longer spans, 40, 50 meters, even more. We've got much more flexible, slender bridge structures. And then on top of those, we put relatively stiff track forms. If we go to ballastless track, a much more rigid, less forgiving track form. And particularly on high speed lines, a requirement for maintaining very high standards of track geometry. So let me go back to basics and go through why this is an issue. And I'm going to talk at the beginning mainly about temperature effects. And I do that, start with temperature effects, mainly because that's a relatively easy one to get your head around, to think through what the implications are, and the rest of it follows from there. So there's a side view of a piece of railway track, continuous rail, sleepers, ballast, the ground underneath it. And the important starting point for all of this is to note that continuous welded rail does not expand or contract. At least it shouldn't. So whatever the temperature is, the rail stays the same length. We constrain the rail so that the effective temperature is to change the state of stress in the rail, not to change its length. If you've got a bridge, the situation is different. Bridge decks are longer on hot days than they are on cold days. So there's a mismatch in there. So think about a cold day on that same bridge. So the bridge deck gets shorter, and the longer the bridge is, the more the gap will open up. You can plot a graph, if you like, of bridge deck displacement, and it's going to look something like that. So at one end of the bridge deck, we've got a significant amount of displacement. If we put the rail on top, as long as there's enough freedom of movement between the track and the bridge deck, then the track is not affected. So there's no added stress in the rail, no additional stress. And a note here, in which for the rest of the presentation, when I talk about additional rail stress, I mean, if we compare this track on a bridge with exactly the same track form, carrying the same traffic, same track geometry, but not on a bridge, the question is, how much extra stress do we put in due to the presence of the bridge? So when I talk about additional stresses or forces or displacements, it's additional over and above what we would have with the same track form, but not on a bridge. So in real life, there's never enough give to make sure there is zero effect on the rail. What tends to happen is that as the bridge deck moves, it drags the rail along with it. So if we plotted rail displacement, we would get a curve something like that. It's not going to move as much as the bridge deck does, but there will be some displacement of the rail. Again, bearing in mind that the rail is fixed in overall length, that's going to generate a stress. So we do get an additional rail stress, which is proportional to the slope of the displacement graph. And the key effect of that is that we will get a peak stress in the rail directly above the point at which the bridge is moving, the structural movement, joint, abutment, whatever it might be. So in terms of temperature changes, we expect a pattern something like that, depending on the exact bridge, the exact track form, which will tell us, which will generate a peak stress above the movement joint. I'm not going to go through traction and braking forces in detail, but effectively, if you hit the brakes on a train or you accelerate hard on the train directly over the bridge, you get a similar effect, but it's the reverse. That this time the train drags the rail, which drags the bridge deck. But it will have the same effect of putting a peak stress in just over the. Just to think about, I've talked a lot about how much give there is, how much freedom there is for the rail to move relative to the bridge deck. And we can quantify that. Theoretically, we could do a test and push a piece of rail on its sleeper, in its ballast, or on its concrete deck, however it might be set up. And we can generate a graph of force against displacement. And it will be something of that form. Varies according to principally whether it's ballasted or not, but also according to the type of fastening, type of sleeper, and so on. In many of the standards, that graph is approximated by a bilinear curve, something like this. So the assumption is that there is an elastic displacement up to a peak value of displacement, which is indicated by U0. and that then thereafter the rail or the track can move freely at constant force. So a couple of little notes there. If you go into the standards, you find this terminology. So U0's the maximum elastic displacement. If you're analysing a very long bridge deck with ballastless tracks, a very stiff track form, you can get a pretty good approximation by saying U0 equals 0. I wouldn't recommend that for final calculations, but for initial scoping calculations, it can save some computing time. But U0 has a value in all cases, whether you can ignore it or not. And then the value of K, we've had long debates on European committees about the way we've indicated this, but K is the force per unit length of track. So it's a total force in 2 rails. The units are therefore in kilonewtons per meter, and it's called K, but it's not a stiffness, it's a force per unit length. So if you get into the standards, that's worth keeping your mind on that. I've talked about temperature changes and traction and braking forces. There is a third source of stresses in the rail on a bridge, and that's bridge deck end rotation. So take a bridge like that, focus on the abutment, and think about, well, if we put a vertical force down on the bridge deck, that's going to generate some movement, which in turn generates tension and uplift of the rail, and it, once again, concentrated right over the movement joint. So it's right where the other stresses are at their highest. I will mention later a bit about the responsibilities of track designers versus bridge designers and all this, which is a subject for a whole new presentation, if you like. But one thing worth pointing out at this point, the distance between that pivot point and the rail is critical. If you take a simple solution like that, the bridge bends, we get that joint opening up by a significant amount. A change to the detail design of the bridge end, moving that pivot point closer to the rail, can reduce that amount of movement very substantially. That's the kind of change which may be possible at the early stages of the bridge design and is generally impossible at the late stages. So the sooner you start thinking about track bridge interaction when you're designing a new bridge, the better for the design later. Where does this sit in the standards? As you're probably all aware, the Eurocode is in the process of turning into the so-called Second Generation Eurocode, and the relevant bit was actually reissued in, I think, November of last year. So the bit which covers this issue is in EN 1991-2, and I'm going to be talking about the 2023 version of that, which is the second generation version. So it's buried in a document which is about traffic actions on bridges, although there are bridge interaction stresses even without any traffic. And in that Eurocode, there is a section 8.5.4 about track bridge interaction, although the standard calls it combined response to variable actions. Because it is 8.5.4, it sounds like one paragraph with maybe a footnote buried at the end of the standard. It's actually 12 pages long, so there's a fair amount in there. The information in there can be traced back to a UIC leaflet, the UIC 774-3, which was written in the 1990s, last revised in 2001. And the CEN committee or CEN Task Group that I chaired in 2015 to 17, we did a sort of state-of-the-art review then and published that in a CEN technical report in 2018, and that has fed into this second generation version of the Eurocode. So if you are going to get into this subject in detail, you need that section of the Eurocode. It's still useful to look at the UIC leaflet, and it's worth having a look at that technical report, which is about 100 pages long. Actually, there's quite a lot in there. So there's a assumption in all of this that the acceptable value of this additional stress in the rail could be determined by the track authority. So the question of how much additional stress you can put into the rail by virtue of putting a bridge there is a matter for the track authority. In the standard, there is an example of the values which are associated with a typical bit of high-speed track or mainline track. And it is only an example. So the implication of all of this, and it's covered by various little footnotes and other notes in the standard, is that if the track is not the same as in the example, then the track authority should be consulted. And I know part of the problem is when you go and consult the track authority, they say, I know nothing about this. But by implication, the authority should either say, yes, these values in the example in the standard are okay, or they should set some different values which are appropriate to each project. So what happens? How does this all work? The maximum stress that can be tolerated by the rail depends mainly on the properties of the steel. It's a beam in bending or a beam in tension and bending, which can be treated as a structural element, and the fatigue of that is mainly determined by the fatigue resistance, determined by the properties of the steel. There's a stress in the rail, which we can call the applied structural stress, which occurs under traffic, even if there is no bridge. And that will depend on the actual load of the train that's passing over, distance between sleepers, the size of the rail, the alignment of the track, dynamic effects, lots and lots of things. So in principle, the maximum amount of additional stress that we can put in due to the bridge being there is the difference between the stress which the rail can tolerate and the stress which would be applied even if there were no bridge. So it's the difference between those two values. So just think for a minute about what's happening to rail stress away from the bridge. So this is not track-bridge interaction, this is just track. So away from the bridge, the sources of stress in the rail, of structural stress in the rail, are three main elements. One is the fact that the temperature of the rail may not be its stress-free temperature. So as the rail is constrained to have constant length and the temperature changes, it will generate a stress in the rail. There's also residual stresses in the rail due to the manufacturing and heat treatment processes. Those will always be there. And there's the live load stresses applied to the rail by passing traffic. So we can add those together, and maybe there's other things as well. And we can generate a figure which is the stress level in the rail without a bridge being there. In modern track design, this loading case, which is effectively treating the rail as a structural beam, is not the case that determines how big the rail is going to be, how far apart sleepers are going to be, and so on. Those are determined by things like rolling contact fatigue and wear resistance. And as a result, fortunately for us in this case, if you treat rails simply as structural beams, they're actually over-designed. They're over-designed to get the benefits of those other factors. So there is always a margin between how much stress we put into the rail in the absence of a bridge and how much the rail steel can tolerate. So to try to put that in a sort of graphic presentation, you say the maximum stress in the rail is in tension is set by the fatigue strength of the rail with a safety factor applied to it. And in compression, it's the stress associated with track buckling limits, particularly on ballasted track. So we may get a lower acceptable stress in compression. If we look at the rail stress away from any bridge, we've got those three factors I just talked about. There's the temperature of the rail, the residual stresses in the rail, and the stress due to it being loaded by the train. So that leaves notionally the maximum acceptable rail stress which we can apply due to track-bridge interaction. going back to the beginning of the presentation, we said there were 3 factors in that. So if we work back from the other end, we've got an element of additional stress due to the temperature of the bridge. So this is stress in the rail caused by the change of temperature of the bridge. We've got stress due to traction and braking, and we've got stresses due to deck end rotation.
Oh, we did.
Sorry?
Sorry, apologies.
No, okay. If you had a question, then jump in. Okay, carrying on. So those are the stresses we've got. So the challenge for the bridge engineer is to squeeze those elements into the limit, which is supposedly at least set by the track authority. So we can make changes to the design of the bridge and design of the track and so on to try to reduce those track bridge interaction stresses so that we get within the margin between the capacity of the rail and the stress which will be put into the rail even without a bridge. The other thing, actually, I'll just go back a couple of steps in that. It's worth noting, if my cursor works, the temperature of the rail affects the stresses whether there's a bridge there or not. So it's on the green bar. The temperature of the bridge affects the track bridge interaction forces. So we need to be careful to understand what happens because of change of temperature of the bridge structure, what happens due to change of temperature of the rail. Just to note that at this stage. So we go back through there. So what about if we have different track and traffic conditions? The standard, the Eurocode, makes a few assumptions. First of all, it assumes that the loading on the bridge is so-called low model 71, which you're probably familiar with. But amongst other things, low model 71 makes an assumption of a maximum axle load of 22.5 tons. And thereby hangs another 2-hour presentation if you wanted to go through it, but not today. The Eurocode on track bridge interaction makes some other assumptions as well. It assumes we have standard gauge ballasted track. It assumes that we have straight track or very large radius curves. It assumes we have 60 kilo rail, that we have concrete sleepers of a reasonably high mass at 650mm spacing, and it assumes that the grade of steel for the rail is R260 or better, so 260 hardness or better. So the question which we need to face up to is, well, what happens if that doesn't describe our railway track? How do we deal with it? And so I'm not going to go through the details of the calculations, but I do want to go through the sort of principles that we need to have in mind when we deal with these things. So if we've got different track configurations, the bridge engineer should go to the track engineer and say, what do I do about this? And it's particularly an issue for urban railways, where we are increasingly dealing with quite long span bridges, quite flexible bridges. Again, a lot of ballastless track. So there's examples here with steep gradients, very sharp curves and so on. How do we deal with all of those which are not described in the standard? Changing axle load is generally good news because most of the applications we're looking at, particularly on urban rail, have lower axle loads than 22.5 tons. So that has an effect because that part of the green bar, that part of the rail stress even away from the bridge, gets reduced. You also get a bit of benefit on things like bridge deck end rotation, traction and braking forces by reducing axle loads. So that gives us a wider gap. So generally speaking, urban railways, we should be able to tolerate higher stresses in the rail, higher additional stress in the rail than we do on high speed lines, for example. But just keep that thought in mind for a moment because it's not all good news. Ballastless track, we get some advantage as well because the effect of track buckling is usually negligible. So the margin we're allowed for compression stresses in the rail is likely to be higher for ballastless track than for ballasted track. That can also imply changes in track stiffness, which generally are going to be beneficial. So again, going to ballastless track tends to allow us a bigger margin as to what stress we can tolerate in the rail. But so those are the two that are good news for urban railways. For other things, the other assumption in here is that the track is straight or a very large radius curve. A bit of a mouthful of text here, but basically the track curvature has little or no effect on the track bridge interaction forces. That assumes that the rails have a reasonably uniform lateral support stiffness. So if there's a change of lateral stiffness as you go across a bridge abutment, for example, that can generate some track bridge interaction forces. So as far as the red bar is concerned, curvature is not really an issue. However, even on track away from bridges, we get higher rail stresses in curves because the lateral forces give us torsion and lateral bending. We get out of balance forces in curves and so on. So the main effect of track curvature is to increase that bit of the green bar. So that's now closing up the gap that that we've got to work in. So generally speaking, for our lighter trains on urban railways, we get benefit because we've got lower axle loads, but we get a disbenefit because we've got curves. There's some other things in here. I won't go through everyone in great detail. There's an assumption of 60 kilo rail. Using lighter rail sections, again, can increase the stress in the rail, whether or not there is a bridge there. Changing support spacing has a similar effect. So again, those things can close up the gap and give us an extra challenge of how we deal with the available stresses. And the bit about rail steel grade, just to throw this one in, which is mainly a track engineer's problem rather than a bridge engineer's problem. The Eurocode says that it assumes R260 or better. The assumption is that if you go to harder rail, the rails are designed, or the steel is, and the heat treatments are designed to give better rolling contact fatigue resistance or wear resistance, and they don't necessarily give you better bending fatigue increases. So the assumption of the standard is that once you get harder than 260, the bending fatigue resistance is constant. If you can show that your rail does have better bending fatigue resistance, then you could argue for higher stresses. So that's what that's all about. If your rail is less than 260, then the assumption would be that the fatigue resistance would go down, and you would need to reduce the stresses. But to be honest, nobody is using softer steels than that in new track construction. So that lowering the strength of the steel would give us a reduced margin. Well, can the track engineers do anything about this? Because the bridge design, clearly all of these things, by changing the span lengths of bridges, changing the stiffness of bearings, all of those things can affect how much these stress is put into the rail. What very often happens is that the bridge is almost finished, or you're dealing with an old bridge and putting new track on it. And the question is, what can I do at the last minute to change it? Can I do things in the track design? So the first thing to say is optimizing the bridge design has a much bigger effect than anything we can do in the track design. So the earlier you think about track bridge interaction in designing a new bridge, the better. However, there are some things that can be done, and just to go through these briefly, keeping one eye on the time. Of course, we can just put expansion joints in the track, and that's been done for many, many years, and it still has to be done in many cases. There's a couple of examples there of joints which are going to allow the rail to move. I have yet to meet, in many years of dealing with track engineers, I've yet to meet any track engineer who likes maintaining these things, because they have to be maintained so they're free to move. Whatever, any shortfall in the maintenance, they generate impact loads as the wheels run over them. That disturbs the ballast and causes all sorts of other problems. So rail expansion joints are possible, but are not liked. On high-speed lines, they are a real problem. And the kind of quality of track geometry on high-speed lines, expansion joints become very expensive, very sophisticated pieces of equipment. And if we can minimize the number of expansion joints, that's all good news. There's a couple of examples of expansion joints on ballastless track. A couple of things to point out here. There's the left-hand one, which I think is on the metro in Washington, D.C., WMATA. You can see where I've got the cursor there. That's where the bridge has an expansion joint, bridge structure has, which is not easy to see. And what the engineers have done here is put a rail expansion joint directly over where the bridge moves. Again, you can do it. It all works on day one, but you're now got the risk, if the maintenance is not perfect, of generating impact forces directly over the weak spot in the bridge, which is not great news. The one on the right is the extreme of what you can do here. This is actually the end of a 2-kilometer long suspension bridge, the Qingmao Bridge in Hong Kong. All of the expansion of the bridge takes place at one end, so you've got potential movement of plus or minus just over a meter. So this is an expansion joint which allows the rails to move by a total of 2.2 meters. A very sophisticated piece of engineering and something which has to be maintained to quite a high standard. That's on a 140 kilometer an hour speed limit, I think. So an expensive piece of equipment. So it can be done, but we prefer not to do it. There's other things we can do in the track. One of them is to reduce the amount of restraint that we apply between the rail and the bridge deck, particularly on ballastless tracks. This is going to give us a chance to just let the rail move a bit. And this one is one example from my days of working at Pandrol. The one on the left is a standard rail fastening clip. The one on the right fits into the same housing, same base plate, but we've made the clip out of a smaller diameter of steel bar, which means it's a softer spring and has less force applied to the rail. There are even cases, in this one, we actually have a plate put in which holds the rail clip, slightly exaggerated in this picture, but holds the rail clip clear of the rail, so that while the rail is not being lifted up by any forces, it can slide freely through the rail fastening. So what we call a zero longitudinal restraint fastening. The potential application for those, well, one thing we can do is it's not a very good illustration of what this is supposed to be showing, but effectively we can stitch the rail down onto the bridge deck tightly at midspan and allow it to, so midspan here we'll have the rail fixed to the bridge deck, and then near to the structural movement joints we can put in these sliding fastenings which allow some movement. The effect of that, this is a bridge, this is actually on a metro system in Bangkok, but when we did it, looked at the stresses in that bridge. This is the one example I'll give today of what the stresses actually look like on a real bridge, but the light blue line on here is the additional stress in the rail. And you can see that where there is a structural movement joint in the bridge, we get a peak stress in the rail. And here we've got a value of 106 megapascals. The design limit in this case was 92. So we were close, but over the limit. So by putting zero restraint fastenings in just across the joint area, we've actually taken that peak out of the rail stress and given ourselves a lower limit, got ourselves under the specified 92, which we had in this case, down to 88 megapascals. So there are tricks we can use in the track which will allow us to reduce the stresses in the rail without actually cutting the rail. Just a warning on that particular one, there's a limit over about how much track you can leave free to slide. In most railways, there is a limiting value of the gap which would open up if the rail broke. And it's normally somewhere between 50 and 100 millimeters, or in America, 3 inches. So it's of that order. So if you have too much rail which is free to slide and the rail break, you would end up with an excessive gap, which would not be permitted. And another little trick here, just to I'll wrap up at this point because we're getting to the end of time. But the other thing you can do, thinking back to that picture in Washington, is use zero restraint fastenings to optimize the position of the rail expansion joint. So by putting full clamping force fastenings either side of this, and then sliding fastenings between the structural movement joint and the rail expansion joint, we can actually position the rail expansion joint away from that joint, give it a better support, and minimize the effective impact loads. So that, I think, brings me to about 1:15, which was my intended time. So we'll invite some questions, and if you want to contact me directly, there's an email address there which will get to me. Otherwise, thank you for listening. Let's return to my other screen. I can do that.
Thank you, David. There's a couple of questions in the chat. I don't know if you can see them,
Right.
David.
I can, yes.
Yeah, if you have a quick look at them, and then we'll
Right.
ask for any further questions.
Climate change, yes. The climate change thing, it's a biggie, actually, that one. Whether or not there's a bridge there is an issue about the effect of climate change on dealing with stresses in continuous welded rail. I was actually involved in a project at Southampton University a couple of years ago looking at exactly this issue. I don't think there's a 2-minute answer, but clearly the temperature ranges for both the bridge and the rail, which we have to take into account, are going to change. So there's two issues really. One is about what can we do to minimize or to tolerate, should we say, a higher stress range in the rail. The other is going to be how we deal with potentially bigger movements of bridge decks. So I don't think it's a simple answer, but it is an issue and one which we need to keep in mind. The other thing which comes out perhaps with that one is that there is a question about, well, what is the temperature of the bridge? And the standards assume that there is one number that you can put in the calculations, which is the temperature of the bridge. And I think anyone who's worked on any kind of concrete structures in particular knows that depending on where you measure the temperature, it varies. So there is a bit of research work going on at the moment about deciding how you measure the bridge temperature. I think that feeds back a bit into this thing about climate change, because it becomes clear that there is a difference in the effect of daily temperature range compared with short-term temperature changes for the weather and so on. So it's a big subject, and I don't have a quick answer. Moving down, the other question here, distance between the deck bearing and the deck end. Okay. So that has been taken into account in the HS2 bridges. If that's my understanding of that, that's all really good news, because it does make a substantial difference. I say if you wait until 5 minutes before the bridge is being built and you ask the bridge designer to move the dip bearing, the answer is usually impolite. Are there more below? Oh, there are some more below that. Is there any formula or study on the reduction of allowed? No, there isn't. Not formally, and I think anyone who's looking at potential for doing any research in this area, that's one that can be done. The original calculations that were done for straight track are now published. For many years they weren't. They were in a Deutsche Bahn internal document. They have now been published, although only in German. But there is a basis there for someone to rework the numbers for curved track. Validation testing, there's not enough been done is the answer. And one of my frustrations of dealing with this subject for many years has been that people will spend millions of pounds building a bridge, and then you say, well, let's spend a few thousand more to instrument the joints and see what happens, and that rarely gets done. So I can't give any quick references to validation testing. There is some from the 1970s, and I know there is some been done a bit more recently in South Africa. So I can't give a lot of help on that. Not in 5 minutes. The magnitude of rail compression, additional stress for direct fastenings. Yeah, the revised Eurocode, the advice in there is that you consider it to be the same as the tension value, the limiting value to be the same in compression and tension if you have ballastless track. Effect on increasing ballast and sub-ballast stiffness through stabilization and rigidity. If you can do anything to increase the longitudinal stiffness of the track, that's great. Many of the things which increase stiffness vertically have very little effect. Again, that's a quick answer to a complicated question. Should lower toe load clips generally be used across multiple run on bridge decks rather than higher toe load clips? Depends on the particular track design. The Japanese track form, which is used on their high-speed lines, they do actually use low toe load clips, low clamping force clips on the whole length of the track. In European applications, it's tended to be either full toe load or zero. So yes, you can go either way with that, but it does depend on the detail of the design. I'm certainly interested to keep in touch with what's going on with RSSB. I mean, I've had a fair amount of contact with RSSB over the years on this subject, so happy to see what's going on.
Yeah.
I think that's all the comments.
Certainly, yeah, RSSB are looking at this at the moment.
Yes.
If anyone, just the earlier comment that someone had made about the instrumentation and validation, if anyone's got any structures that they're starting to look at that this in the UK, should we say, that this is a key topic, can you let us know, because there may be an opportunity to get some funding for R&D and get some instrumentation on some structures of the track. Certainly, if I wish we'd done it 10 years ago when we built hitching, because I think we could have had some really interesting data out. So if there is any opportunities, I know there's one on TRU that people are looking at the moment, but if anyone can think of any more or identify any more, then give me a shout.
It's all good news.
Thanks, Paul. Right, I think we'll call it a day there. I'd like to thank everybody for dialing in. We've had over 250 people dialing in, and it's great that we're generating this sort of interest. And I think these lunch and learn sessions seem to be working, so we will certainly be carrying on with this. I know some of you have already put some reactions up and some hand claps and thumbs up and whatever, but if I could ask you to thank David for his presentation and show your appreciation in the usual manner. Thank you, David.
That's my pleasure.
Thank you.
Thank you.
Thank you very much, David.
All right, thank you.
Thank you.
Have a good afternoon, David.
I will.
Thank you.
Thank you.
Thank you. Bye bye.
Yeah, cheers. Thank you, David.
Right, David, thank you.
Thanks, everybody. Thanks, Dave. Thank you, everyone.
Thank you.
Thank you very much.
Right. Right, bye, everyone.
Thank you, David.
Yes, so thank you very much, David.
Thanks, David.